All right, now the next step with magnetism and starting to bring in the electrical piece. And you're going to start to see the actual link. I already alluded to it last section where we talked about the magnetic field being created by these electrons spinning in a certain orientation. So we have electric charge moving. And if you think back to our electricity unit and Ohm's law and voltage current resistance, current is the flow rate of charge. So if magnetic fields are somehow linked with moving charge, current should be thrown in here somewhere as well. This is going to be kind of, this whole unit is one of the ones I'm really going to miss teaching to you live and doing some neat demos because it's really cool doing some of this stuff and, kind of giving you some things to think about. So try my best. I've included some videos. I'll allude to some videos. I found some that, do similar demos that I'd like to do with you, and hopefully we can get through this. Just again, miss the interaction, but we'll get through it here. So what you see here on the screen is an image. The one on your left here is a bare wire, has current going through it, and you have iron filings. Iron is magnetic. And so what you see here is you can start to see these, what we call these concentric circles. And if you've ever seen the old trick of dumping the iron filings on top of a magnet, you'll see that the iron filings always line up to the magnetic field lines, and you start to see these patterns, and that's what you start to see. If there was no current running through this wire here, you would not see these circles, and they would just be random. Okay, this is the one I missed doing in class. Is we strip away the insulation, so you get a bare wire here. You have current running through here, and you start to see these magnetic, the compasses orient themselves on that circle. And so you start to see this concentric magnetic field, these circles of magnetic field being created. Now the cool thing is, and you'll see this in the video that I've linked later, is that as soon as you turn the battery off or throw the switch open and there's no current going through here, the compass will actually line up to the Earth's magnetic field. Throw the current on, you'll see them align and spin and point in the circle. If you switch the polarity of it, so negative to positive, you'd see them all orient themselves the opposite way. So it's kind of cool to see. If you've ever been out hunting or not, well, that's when I've observed it. But if you go underneath like high power tension lines, the big tension power lines, and you're trying to read your compass, you actually see this effect happen out there, and your compass is not any good as long as you're standing anywhere near those or underneath them. They're actually creating a magnetic field of their own. So here you can see the effect that we're going to talk about today of, if you have current going through here, a wire, current is moving charge, create a magnetic field. So if we back up to the targets, just kind of again, this is the next step here. We're going to describe magnetic fields produced by current in a straight conductor, and then something called a solenoid. Solenoid is just a coil of wire, fancy name for a coil of wire. We're going to use something called the right hand rule. That's another thing I'm miss showing you because you all kind of sit there and try to curl your hands and mess with your hands. But the right hand rule, great video I showed in class as well, but I also do the demo with you and show you, is going to help show you based on how the charge is moving, how was your magnetic field being created. And it's called the right hand rule because we're going to use parts of our right hand. So a long straight current carrying wire, easy to say, creates these concentric cylindrical magnetic fields. Okay, and you saw that in that last example. You have current going through here. Charges are flowing up or down. It's hard to tell. You can't tell in this image here. And you start to see these circles being created and these iron filings matching up. What we talk about is that there you are causing a current is creating or inducing a magnetic field in its surroundings. And I alluded to this. If you would reverse the polarity or the direction the current is flowing, you would see those needles flip flop. So there is a very direct relationship between the direction that the current or the charge is flowing and how that magnetic field is being created. So where your north-south pole is being created is going to be determined based on the direction that that current is flowing. These two videos, obviously, I'm not going to show them here, but they're linked to off of Classroom, off of your cheat sheet. They're also here on the raw form. Please take a couple minutes to watch both of them. They will show you those demos and explain them as they go. All right. So the right hand rule, again, it's called the right hand rule because you're using your right hand. It is going to help you determine the direction of the magnetic field. Your thumb will always go in the direction that the current is going, and your fingers will curl in that direction around. In this case, we're using this for a wire, will curl and show you the direction of the magnetic field lines. Okay, so here you would see those magnetic field lines going around, you see around and around. Okay, but you see the direction that the magnetic field lines are going. Okay, now later, what we're going to talk about is so, like at this instant here, this would be like creating a magnet with a magnetic field line vector like this. Over here, at this instant in time, you would have a bar magnet that looks like this. Okay, but you can see the curling of your fingers around that wire is going to give you the direction of the vectors. Thumb is going to go in the direction. So you can see that if I alluded to flipping the polarity, the current would be going the opposite way. Your thumb would be going down. Your fingers would actually be curling the other way, and you'd see the needles of each one of the compass flip around and point the other direction. So the right hand curl rule, a lot of times you'll hear it called. It's going to show you the magnetic field lines, how they curl around a current carrying wire. The right hand curl rule. Thumb in the direction of current, flow charge, and the fingers are going to curl in that direction. All right. So a solenoid, and this is where we start to get kind of interesting and you start to see in some of the applications. Again, a solenoid is a fancy name for a coil of wire. You know, a coil of wire, you're looping it around, you have a hollow circle. Um, there is later when we start talking about transformers, motors, generators, there is a relationship between the number of coils or loops that you have. Okay. This is one loop. Now, most of the time, you're going to see many, many coils of wire. You see these in alternators on cars, again, any motors, generators. We create these with electromagnets. Oh. But if you look at what's happening, and it's hard for me to show you right now, because I'm not there. But if you put your thumb, so if I put my thumb in the direction of current, let's use blue for my thumb. Try it as best I can. Okay, so my thumb is in this direction, going up because the current's going this way. My fingers would curl. Actually, let's back up. Let's do it differently. Let's use our pink here. So my current right at that instant would be in that direction, going out. My fingers then in the blue would curl around there. So if you just take that cross section right at that little area right there, just like our current carrying wire, you would see that curl. Okay, back here, again, if you did the same thing at that instant in time, my thumb would be going in that direction. It would curl out and my fingers would come up in the middle there. Over here, if I did the same thing, oops, my thumb would be kind of coming out of my page and I would see my fingers curl. But no matter where you are on this loop, and I really recommend you try this, your fingers are always going to curl up through the middle. So what you're creating is a very well-defined uniform magnetic field in the middle that would look like a bar magnet inside, an electromagnet. Okay? Now, the more loops you're going to have there, you're going to have more field lines, higher flux, stronger magnetic field. Okay, that's the power, and that's kind of the whole thing behind coils or loops of wire, or again called a solenoid. So again, if you double that, you're going to have more moving current. You're going to have a stronger magnetic field, and so it is going to be a relationship between the length, the area, and the number of coils you have, as well as the flow rate, the current. And we'll talk about that next chapter. Okay. Here you can see more typical of what you might see with a true solenoid. Again, all you did was have that loop just stacked over and over and over and over again. So every time, okay, it's going to loop and come back, loop and come back. So we can only see one side of it here. But at every instant in time on this side of the coil, the current is moving in this direction. Okay? So if you put your thumb up there every single time, it's going to show you that it's going to come and wrap down through, down through, down through. So you're creating a very, very strong, in essence, temporary bar magnet as long as that current's going. Now, if you switch the polarity, okay, it would be going in the opposite direction, and the North Pole would be over here. So what is the shape of a magnetic field produced by straight current carrying wire? Again, right at that instant in time, thumb goes in direction of current. Your fingers are wrapping around. They're creating those concentric circles like you saw with those iron filings. You also saw it with with all the compass lined up around there. So why is the magnetic field inside a solenoid stronger than the magnetic field outside? Okay, you're getting a confined area, and you're getting it to add up. You're getting all these field lines shoved into a small area. They're all in the same direction, so they're netting up. They're not canceling each other out. They're adding up and creating that very uniform area. And that last diagram I showed you was a great, great example. If electrons behave like magnets, then why aren't all the magnets, all atoms magnets? Okay, most of the time, those electrons aren't free to spin as they want or be manipulated very easily. And usually you talk about them finding them in nature spinning opposite and paired up. Now, here, so I told you we'd come back to this one. Torque coils. Okay. A lot of times you'll see these in um, satellites to orient themselves in certain situations, or to line them up and keep them lined up, say the satellite pointing towards earth and not all. Or you got the Hubble telescope, how does it orient? It doesn't have rockets on it anymore. Okay, it has solar panels for the electrical work. So what does it do? It has those solenoids, those coils of wire, they're called torque coils on there. The earth has a magnetic field. Okay, so if I go back here and I have these coils, okay, and I all of a sudden I flip the switch on and allow electricity to go in, okay, I can use the Earth's magnetic field and my bar magnet, and I can use those two, because what happens when you have magnets, you have a force, right? So now I have the Earth's magnetic bar magnet, if you will. I have this bar magnet, and I can manipulate my magnet here with a solenoid. I can change the strength. I can change where the north south pole is. I can play off the Earth's magnetic field and align myself and use that to apply a force to orient my satellite the way I want to. Okay, I can vary the strength, the flow of current. I can change the polarity. So I can use these temporary magnets to, in essence, steer and orient myself. So that's what's it's kind of neat. So as always, again, if you have questions, make sure you ask. Make sure you understand the right hand rule, the curl rule. Make sure you take a look at those two videos, especially that show the demos. They're really nice. I try to kind of walk through them with some pictures, but it doesn't do it justice. So take a look at those. The next phase is we're going to start kind of putting all this together. You're starting to see how this meshes, But the last piece is kind of the last piece of the puzzle before we get into the motors and generator.